This problem is about choosing which automation projects to invest in and when to implement them. Automation decisions affect cost, throughput, reliability, and long-term competitiveness, but outcomes are uncertain and projects interact with each other. In this chapter, we treat automation investment as a portfolio decision. We combine financial value, risk, implementation complexity, and strategic positioning so that the final plan is not only profitable on paper but also feasible to deliver. Consider a major container terminal evaluating a $50 million automation initiative. The portfolio spans autonomous cranes, AI-powered yard management, predictive maintenance systems, and integrated digital twins. The decision requires understanding implementation costs, operational savings, technology maturity, integration complexity, and competitive positioning. Because these factors evolve over time and influence one another, a static single-number return on investment view is often misleading. Traditional return on investment analysis assumes stable, predictable outcomes. In automation, benefits are uncertain, adoption is staged, and integration risks can reduce or delay benefits. Automation technologies also interact. For example, yard optimization may unlock more value only when crane automation is also deployed. This interdependence means you need a model that can represent uncertainty and synergy explicitly. We will move through multiple tiers. Tier 1 provides a multi-period stochastic programming model for project portfolio selection. Tier 2 uses a priority-based heuristic for fast decisions. Tier 3 uses particle swarm optimization for deeper search. Tier 4 uses deep reinforcement learning to learn timing strategies. Tier 5 uses a system of systems digital twin for ecosystem-wide simulation. Tier 7 focuses on a human and AI partnership, and Tier 8 integrates ethics through value-aligned constraints. Tier 1 models the investment decision across multiple periods and multiple scenarios. You decide which projects to select and how quickly to implement each one over time. The objective is to maximize expected net present value across scenarios while also capturing synergy between project pairs. Constraints include the overall budget, implementation logic, gradual ramp-up limits, and mutual exclusivity for certain options. We define a set of projects, a set of time periods representing the planning horizon, and a set of scenarios representing uncertainty in market and operational outcomes. These sets allow the model to represent both timing and uncertainty, which is essential for staged automation deployments. Key parameters include the initial capital cost for each project, operational cost savings over time under each scenario, and revenue impacts under each scenario. We also include scenario probabilities, a discount rate, a total budget, and synergy coefficients between project pairs. Together, these parameters represent both direct financial value and interaction effects. A binary selection variable indicates whether a project is included in the portfolio. A continuous implementation variable represents how much of the project is implemented in each period, from 0 to 1. This enables modeling gradual adoption, integration ramp-up, and staged rollouts. The objective maximizes expected net present value. For each scenario, the model adds discounted operational savings and revenue impacts multiplied by implementation level. It subtracts the upfront capital cost for selected projects. Then it adds synergy terms that represent additional value created when certain projects are selected together. The budget constraint ensures total capital investment stays within the available budget. Implementation requires selection, meaning you cannot implement a project you did not choose. A gradual implementation constraint limits ramp-up to at most 0.3 per period. A mutual exclusivity constraint prevents selecting more than one option from certain categories, such as crane automation choices. This diagram shows the portfolio structure and the interaction pathways among projects. It is a visual reminder that automation is a coupled system. Operationally, the diagram helps stakeholders see why synergies matter and why a portfolio approach can outperform isolated project selection. The example includes 3 projects with capital costs: autonomous crane system at $20 million, AI-powered yard management at $15 million, and an integrated digital twin platform at $18 million. The budget is $50 million. Uncertainty is represented by three market scenarios: high growth at 40% probability, base case at 40%, and low growth at 20%. The expected annual benefits depend on the scenario. Project 1 has 8 million in high growth, 5 million in base, and 2 million in low. Project 2 has 6 million in high, 4 million in base, and 2 million in low. Project 3 has 7 million in high, 4 million in base, and 1 million in low. There is also a reported synergy between projects 1 and 2 of 15% additional benefit when both are selected. The reported mathematical solution selects projects 1 and 2. This uses $35 million of the available budget. The reported expected net present value is $47.3 million over 10 years, and it captures the synergy effects between the two selected projects. Tier 2 provides a fast approach for screening large portfolios. Each project is assigned a composite score that combines risk-adjusted return, strategic alignment, complexity, readiness, and synergy potential. Projects are ranked by this score, then selected in order while respecting the budget. This gives real-time decision support even when the project list is large. This code defines a project structure with key attributes such as cost, expected benefits, risk factor, strategic value, complexity, technology readiness, and a synergy matrix. It also defines a risk-adjusted net present value calculation, discounting annual benefits and reducing them based on risk. This section defines the composite score. It weights multiple criteria, including a return component, strategic value, technology readiness, ease of implementation, and risk mitigation. This scoring approach is designed to prevent over-investing in projects that look profitable but are too risky or too complex to implement effectively. This section implements greedy portfolio construction. It sorts projects by score and then selects projects while budget remains. It also adds synergy benefits when a newly selected project interacts positively with previously selected projects. The output is a selected project list and total portfolio value. This diagram summarizes the heuristic workflow: compute scores, sort, select within budget, and account for synergies. It highlights the practical appeal of this tier: rapid portfolio selection with explicit multi-criteria reasoning. For the example with a $50 million budget, the heuristic selects AI yard management, autonomous crane system, and predictive maintenance AI. The reported total investment is $47 million, and the reported portfolio net present value is $89.34 million. The reported complexity is on the order of n log n due to sorting. Tier 3 uses particle swarm optimization to explore portfolio combinations more thoroughly. Each particle encodes a candidate portfolio as a multidimensional vector. The swarm updates solutions using personal best and global best information, balancing exploration and exploitation. Budget feasibility is handled through penalties so that infeasible portfolios are discouraged. This code defines a particle with a continuous selection vector and a velocity vector. Fitness evaluation thresholds the selection vector into binary project inclusion, checks budget feasibility, and computes portfolio net, present value with risk adjustment and strategic bonus. This section computes synergy benefits between selected project pairs. It adds additional value when the portfolio includes interacting projects. It also adds a diversity bonus when multiple projects are selected, encouraging richer portfolios when they remain feasible. This section updates particle velocity and position using cognitive and social terms, then clamps values to keep them within valid ranges. By iterating these updates, the swarm shifts probability mass toward portfolios that consistently produce higher fitness. This section runs the main loop over iterations and updates personal best and global best solutions. It also decays the inertia parameter over time to transition from exploration to exploitation as the search progresses. This figure visualizes swarm behavior and solution evolution. It highlights how the swarm can discover portfolio combinations that a greedy heuristic might miss. The main value is exploring nonlinear synergy structures and discovering high-performing combinations under constraints. In the reported PSO example, there are 6 projects and a $60 million budget. The selected projects include AI yard management, autonomous crane system, predictive maintenance AI, and autonomous vehicles. The reported total investment is $72 million. The reported portfolio net present value is $156.73 million, and reported budget utilization is 95%. The key lesson is that meta-heuristics can search wider, but constraint handling must be carefully designed. Tier 4 models investment as a sequential decision problem. Instead of selecting everything at once, an agent chooses projects over time while observing market and technology maturity. The state includes market conditions, available budget, maturity levels, competitive position, and current portfolio. Actions include project selection and investment timing, and the agent learns strategies through reward feedback. The reward function balances financial value and strategy while penalizing risk. It rewards net present value increase and strategic value gain. It penalizes risk and adds bonuses for synergy when compatible projects are selected together. This code defines an investment environment. The environment state includes normalized budget, project selection flags, maturity levels, and market volatility. Each step selects a project if feasible, updates budget, updates project maturity, and returns a reward designed to represent risk-adjusted value and timing. This section defines how the environment computes reward using discounted benefits, risk adjustment, and strategic and synergy bonuses. It also includes a timing bonus that rewards investing in ready technologies earlier when time pressure is high. This section defines the deep queue network architecture used to estimate action values. It uses multiple fully connected layers with nonlinear activations and dropout, producing one queue value per possible project action. This section defines the DQN agent with a replay buffer, epsilon greedy exploration, and a target network. The agent stores experiences and trains on sampled batches to stabilize learning and reduce correlation in updates. This section describes the replay update, where target values are computed using the target network and the loss is computed using mean squared error. Epsilon decays over time, so the agent gradually shifts from exploration to exploiting learned investment policies. This section outlines the training and testing loops. The agent trains for 1,000 episodes and then is evaluated on test episodes. Scores and selected projects are logged to demonstrate learned strategies and stability. This figure illustrates the agent and environment interaction loop. It highlights experience replay, the queue network, and the target network. Operationally, this approach can adapt investment timing strategies when market volatility or technology readiness changes. After 1,000 training episodes, the DQN agent shows learned behavior. At episode 900, the reported average score is 89.34, and epsilon is 0.045. A reported test score example is 94.67, and the reported average test score is 91.23. The reported selected projects include AI yard management, autonomous crane system, and predictive maintenance AI. Tier 5 uses a digital twin to model automation investment impacts across operations, finance, and strategic positioning. The twin integrates physical asset models, process simulations, financial tracking, and strategic intelligence to assess cascading effects across a supply chain ecosystem. This figure shows the architecture layers: physical asset layer, process simulation layer, financial performance layer, and strategic intelligence layer. The key advantage is continuous assessment. As operational data changes, the twin updates projections, so investment analysis becomes adaptive rather than static. In the example, a terminal evaluates a $75 million automation portfolio spanning autonomous cranes, AI yard management, and predictive maintenance. The terminal context includes 6 berths handling 2.5 million TEU annually, 50 yard cranes, 200 truck gates, and integration with 3 rail terminals and highway networks. The reported results include a 23% throughput improvement, a 31% reduction in vessel waiting times, and an 18% decrease in operational costs over 5 years. The System of Systems analysis also reports $12 million of additional annual value through improved supply chain velocity and service reliability. Tier 7 focuses on human and AI collaboration. Humans provide strategic vision, stakeholder management, and qualitative judgment about organizational readiness. AI provides computational analysis, scenario modeling, optimization, and continuous learning from feedback. Explainable outputs are essential for trust and for resolving disagreements. This figure illustrates the collaboration architecture and the explainability features needed for effective oversight. It includes decision tree reasoning paths, sensitivity analysis, confidence scoring, counterfactual analysis, and feature importance ranking. In the example, a Port Authority committee evaluates a $100 million automation plan. The AI system uses data from 50 similar terminals and evaluates 10,000 scenario combinations. The collaborative plan achieves 95% of the AI-optimized financial returns while addressing stakeholder concerns. The human-guided approach increases stakeholder buy-in by 40% and reduces implementation risk by 25%. Tier 8 ensures investment decisions align with stakeholder welfare, environmental impact, and fairness. The key idea is to encode ethical boundaries as constraints rather than optional considerations. Constitutional constraints can limit job displacement, enforce sustainability targets, and prevent inequitable benefit distribution. This figure summarizes the ethical architecture and how it integrates stakeholder engagement into decision-making. It emphasizes transparency, accountability, and measurable ethical outcomes, not just financial performance. These constraints formalize ethical boundaries. An employment transition constraint limits job displacement based on retraining capacity and attrition. An environmental constraint caps carbon footprint relative to a sustainability target. An equity constraint limits inequality in how benefits are distributed across stakeholders. The ethical objective combines financial net present value with social value, environmental benefit, and stakeholder welfare, while penalizing inequality. This makes the optimization explicitly multi-objective and ensures that financial gains do not come at unacceptable social or environmental cost. A traditional analysis selects a fully automated crane system plus AI yard management, reporting financial net present value of $147 million over 10 years and job displacement of 450 positions, or 60% of the workforce. The ethical framework revises the portfolio to semi-automated cranes plus AI assistance plus retraining. The reported adjusted net present value is $134 million, or 91% of maximum, while job displacement drops to 180 positions, or 24%, with 95% redeployment success. These practice questions ask you to formulate portfolio models with net present value and synergy, implement composite scoring heuristics, and design particle swarm and deep reinforcement learning approaches. They also ask you to describe digital twin architectures and define human and AI collaboration processes, including ethical constitutional constraints and stakeholder engagement mechanisms,